All right, so good morning, everyone, and welcome to 306, Signals and Systems 2. My name is Ahmed Hareedy. I got my, probably some of you have already looked me up, but this is a brief introduction. I have received my bachelor and MS degrees from Cairo University and my PhD from UCLA. I worked with Duke University for some time as a postdoctoral associate, and now I'm a new assistant professor in your department. So this course used to be something a little different in the past. So the way we're arranging this course this year is something else. We have specific goals for you as far as this course goes. We want you to learn some fundamental tools connected to modern applications. In the past, there was explicit focus on certain topics, in particular, autocorrelation, autocovariance, power spectral density, passing random processes through linear systems, and so on and so forth. It's still going to be part of our course, but it's going to be only one of 3 modules. The other 2 modules, as you have already looked up, the first one is going to be a probability review, followed by some essentials about convergence and probability, sums of random variables, and essentials of parameter estimation. And then following that, we will talk a little bit about convex optimization. We will talk about Lagrangians and the gradient descent algorithm, which is essentially the heart of every single machine learning algorithm existing nowadays. We'll talk about the fundamental idea and how it works. And then the second module will go on to discuss more advanced random processes, discrete processes particularly, including the Markov process and the Poisson process. And then the last module is the typical of this course, as we have already discussed. I want the part that has the random processes, the power spectral density, the autocorrelation, autocovariance, and so on and so forth. This is also a different type of course because we will be 3 instructors teaching it, but it's not like every one of us is teaching everything. It's going to be first module for me. The second module will be for Elif Faisal Hoja, and the third module will be for Chagatai Kandan Hoja. So each one of you will get the opportunity to be taught by all of us, by the 3 of us, not just like a specific section for me, specific section for Elif Hoja, and a specific section for Chagatai. Since we wanted to architect this course in a different way, we essentially wanted it to have a different flavor, particularly when it comes to homeworks. Our homeworks will have the traditional mathematical part as usual. We will have 7 homeworks, but some of them, probably 4, you have already the syllabus, probably 4, will have, in addition to the classical theoretical problems, will have a MATLAB problem. The goal of this MATLAB program, there are 2 goals of this MATLAB program. Number 1 is to allow you to visualize things, to see things. For example, it is one thing to write the equation of a power spectral density of a specific sequence, of a specific random process. It's another thing to see it, to write this through MATLAB and see the waveform yourself. The waveform you have already implemented using theory is matching the waveform you are generating through Monte Carlo. All right? This makes a huge difference. This gives you a different feel about the course. The other goal is, of course, a lot of you are, I would say most of you are brilliant students, so some of these projects could also capture your imagination, and why not, you could think of a follow-up project in the future that has more of a research flavor. So this is essentially a general introduction for the course. Do you have any questions before we talk particularly about our module? Sure.
Repeat the lecture for all sections?
Yeah. There is some sort of arrangement that will happen, which essentially is we will not have 3 sections. We will have 2 of them being taught together. We will not have 3 lectures. So the lecture is not going to be repeated 3 times. It's going to be only repeated 2 times, okay? Because 2 sections will be together and 1 section will be unique. I guess your section will be the unique one. This is already big enough, so it has to be unique. Yeah, one more thing. I don't know Turkish, unfortunately. So the lecture, typically the lecture is conducted in English, but I would highly appreciate also if your questions are in English. Otherwise, a friend of yours will need to translate the question to me. Okay. There is some. I'm a new assistant professor. There are things that needs to be settled on the system. However, you can always, like, I can post things through our TAs, and your TAs will be telling you that this is me, but probably you will not see it as me until it is reflected in 2 weeks, okay? But this should not prevent you from always emailing me at hareedy@metu.edu.tr. How about our module? Well, this is kind of weird, but okay. So in our module, we will start with a probability review, as we said. It will be passing by most of the fundamental concepts you have taken in your probability courses, connecting them to what is coming next, connecting them to modern applications as well. We will pass by a number of applications throughout the course, some of them through this part, others through other parts. We will talk a little bit about the applications of what we do in wireless communications, in data storage, in cloud storage, in machine learning, Internet of Things. As we said, we will talk about gradient descent, which is like the heart of machine learning algorithm. We will start by some basic concepts. This is essentially this lecture, which will be a quite light lecture. And because it will be a quite light, I would highly appreciate being interactive. Otherwise, it could be somewhat boring. Hopefully, it will not. Following that, we will talk about random variables, discrete random variables, continuous random variables, expectations, variance, moments, functions of random variables, transforms, more than one random variable, vectors of random variables, and then from that part, we'll talk more about the estimation, fundamentals of parameter estimation that comes from the properties of sums of random variables. We'll talk convergence and probability, and we will talk some optimization. So that's a brief summary of the first module that I will be teaching. Most probably, the first midterm will be only on my module. This is not still 100% sure. Well, at least that's how it looks according to the schedule. Okay, any more questions? All right, let's get started then. So we will start by the definition of a random experiment. What is a random experiment? An experiment in which the outcome changes in a non-deterministic way when it is repeated under same conditions. Things are typically clearer when you contrast them. So when you think about a deterministic experiment, this deterministic experiment, initial conditions are the same, outcome is the same. Random experiment is not like that. Initial conditions can be the exact same, but the outcome varies every single time. Let's do some examples on some random experiments. Example 1, roll a dice and note number on top. Example number 2, toss a coin 2 times and note the sequence. Example number 3, toss a coin 4 times and note number of heads. tails, doesn't matter. And example number 4, pick a real number. Between 0 and 1. Okay, so these are all random experiments that you are quite familiar with, but something that is nice to look at is when you look at example 2 and example 3, when we change this number to 2, so the random experiment, at least how it is performed, it looks the same. But because the outcome is different, the random experiment is seen differently, right? When we look at the sample space here and the sample space here, we will denote that they are quite different, all right? So what is the sample space? So we have the sample point or the outcome. What is the sample point? It is an output of the random experiment that cannot be decomposed into smaller outputs. It's also called an elementary output, an elementary outcome. And by the way, there are many things we will talk about today that they could be useful in things that go beyond, way beyond probability theory. So this definition of something being elementary or something that cannot be decomposed into smaller events, you could see in many other situations, like for example, a prime number, right? So this is also something we will discuss multiple times today. So what is the sample space S? It is the set of all possible outcomes. So we will do these examples as running examples. So whenever we write example 1, we are referring to the random experiment we discussed that the first time we introduced this example for convenience. So please help me with these sample spaces, and let's do them quickly. So S for example 1 is dice number 1 to 6, exactly. 1, 2, ... 6. Let's do the other ones quickly. How about this one? Exactly. But it's 2 times, right? So it's head, 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 tail, tail, head, tail, tail. Head, 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 tail, tail, head, tail, tail. How about the third one? What's up? Exactly, thank you, 0 to 4. You are all wearing masks. It's very hard for me to teach using a mask. So whenever someone is answering something, please raise your hand to know where he or she is, all right? Thank you. And the fourth one is just a set. So S is X such that 0 less than or equal to X less than or equal to 1, which is the closed interval 0, 1. What is the difference between the first 3 sample spaces and the 4th sample space? Yes, thank you, exactly. So this one is continuous and all the remaining ones are discrete. All right, events. What is an event? It is a situation specified by certain conditions that occurs when the random experiment outcome satisfies the conditions. So you perform a random experiment. The random experiment has a set of outcomes combined together in the sample space. The event is particularly a situation that you specify by certain conditions. When the outcome satisfies these conditions, the event occurs. So you could easily see that the event in general, it corresponds to a subset of the sample space. So you can immediately discuss the event as a subset of the sample space. So also the certain event is definitely the entire sample space, and the impossible one is phi. All right, let's do some quick examples as well, just quickly. So what is the event of an even number noted? So A equals 246, exactly. The second one is at least one head observed. How about this one? A equals exactly, thank you. Head, tail, tail, head, head, head. And finally, the number not the number actually, more than 5 tails. Noted, or more than 4 in that matter actually. How about this event? Is it a possible event? No. So it's an impossible event, right? The impossible event is the empty set, right? Okay. Now we will talk about some fundamentals of set theory. Well, actually, it could be better to do them here. What we are going to do right now is I'm going to draw some Venn diagrams, and then you tell me what they correspond to in terms of set theory. All right. This is A, this is B, and this is S. What is this event? In terms of set notations, union, intersection, subset. Exactly, the union. So it's A, union B. How about this one? Thank you. It is A intersect B. How about this one? Thank you, exactly. Is a complement, or as our friend said, A minus, well, sorry, S minus A. Or S intersects A complement, they are all the same thing. How about this one? Exactly, so it's A set minus B equals A intersect B complement. The following ones are not really events, it's just that you are describing the status of the two events. Here we have A and B like that, and here we have A and B like that. What do you think of the left one? This is representing what relation between A and B?
Shows that there is no intersection.
Exactly, they are disjoint, exactly. So A intersect B is phi, or disjoint. How about this one? Bless you. How about this one?
Subset.
Exactly, A is a subset of V. Obviously here you can omit this because it's a strict subset, but okay, we can keep it, that's fine. Okay. Properties of set theory. No. Properties of set operations. Here, we will not really discuss them like one by one. Commutative, associative, and distributive. We'll not really discuss these like one by one, but I want to stop here a little bit and talk about something we have already introduced today, which is there are lots of fundamental concepts we will discuss in this course that relate to things other than probability theory. So here, commutativity, associativity, and distributivity, they are very, very important fundamental properties in mathematical things that you deal with every single day, but you deal with without thinking much about. So in the context of probability theory, so commutativity means that the operations can be exchanged, okay? So in the union, the intersection A union B equals B union A intersect B equals B intersect A. Associativity is that you can associate them together. So A union B union C can be written as A union B together union C, or A union B union C. And distributivity is the two operations distribute over each other. Also operations here are the union and the intersection. But these fundamental concepts, they exist in many, many other things as well. You could think about finite fields. You could think about fields in general, like the set of real numbers, for example. There are certain things you have been using and doing over the years with real numbers that can only be done because the set of real numbers satisfy these. But it's just that you are doing them by default, you are not thinking about them anymore. And they are also very important in defining finite fields, or any set of elements where you can perform operations that are closed under these elements, which is essentially that when you perform an addition or a multiplication between two elements from the field, you get another element in the field, all right? So these are, they go way beyond the course, but since they are quite obvious, quite easy here, we will not really talk about them that much. De Morgan's rules. Those are A union B complement is A complement intersect B complement, and A intersect B complement is A complement union B complement. All right, let's try to apply De Morgan's rule on a simple example from the first random experiment we did. We define an event B as the event of an odd number noted. So it is easy to write B as 1, 3, or 5. Now, let's try. Can we apply De Morgan's law? Can one of you help me apply De Morgan's law on this? A intersect B complement. What exactly will happen here? Just to recall, and put it here. What will happen here?
S.
Exactly. Exactly. Why is that? Because exactly. So it's A. This can be done two different ways. It's phi complement is S, or it's A complement union B complement, and this thing is also S. Correct? Why is that? Because simply A complement is B, B complement is A. Great. There is another fundamental thing that it would be good to discuss here about the logic of proving things. It's also very important and extends Bayesian probability. This is something about fundamentals of set theories that you can use everywhere, in your proofs everywhere. Let's look at X is necessary and sufficient for Y. Have you ever heard about this before or seen it in any of your courses? How many of you have heard or seen this term before? How many? Okay, some of you, that's good. Okay. This essentially means it's also sometimes mathematically written like this. One happens, the other happens. Okay? How can we think about this in terms of set theory? It is essentially set equality. A equals B. A equals B. All right. How can we prove that A equals B? How to prove it? Okay. Side note. When we write that A is a subset or equal to B, what does that mean? Forget about the equality for now. The equality in here is not needed. A means what to B, and B means what to A. If A is within B, is a subset of B, A means what to B, B means what to A. So let's draw it here. A and B. Okay, let's change the question. When A happens, what is this telling about B? The other question is easier. When B happens, what is this telling about A? Okay. When B does not happen, what is this telling about A?
A does not happen.
Thank you. Exactly. So, B is what for A? Necessary. Right. So, B is necessary for A. Without B, there is no A. Right? So, B, necessary for A. How about A for B?
Sufficient.
Exactly. So A is sufficient for B. Because when A happens, it's a guarantee that B happens. So now how to prove necessity and sufficiency is just to prove that A subset of B, B is subset of A. Even this thing is not needed. Okay? This is how you use the fundamental idea of set theory to prove that two events, that two situations are entirely equivalent. They are both necessary and sufficient for each other. Clear? Awesome. And this thing is making weird noise. Okay. Now we will move on to the probability axioms. All right? Probability axioms. There are two axioms. I, the probability of an event A is greater than or equal to 0. Double I, the probability of the sample space as we would expect is 1. And triple I, if A1, A2, up to AN are pairwise disjoint, then the probability of the union from K equals 1 to N AK is the summation from K equals 1 to N, the probability of AK. Obviously here for N greater than 1. What does pairwise disjoint mean? Booster? Yeah, when you pick any two of them randomly, they end up being disjoint, right? How many pairs will you have? We'll talk combinatorics a little bit later today, but how many pairs would you have here? So this is sampling you won't replace, right? You cannot pick the same event, right? And ordering doesn't matter. So how many of them? Thank you so much. It's N choose 2. All right. We will discuss some corollaries. I'm going to be proving the first one, and then together we will be discussing the proofs of the other ones. First one is the probability of A complement is 1 minus the probability of A. The proof goes as follows. A intersect A complement is phi, and thus the probability of A union A complement is the probability of A plus the probability of A complement. And what is this? Probability of A plus probability of A complement. Thank you. Is 1. And thus the probability of A complement is 1 minus the probability of A. Proved. Corollary 2. It goes in line with this one. Probability of A less than or equal to 1. Proof. Any suggestions? How can we prove this thing? I don't know why it went that high. How can we prove this?
By subtracting first axiom concept.
Yes, exactly. It's just that you already have probability of A being 1 minus probability of A complement. And then, as our friend just said, you use this axiom. It's done. This thing is greater than or equal to 0. So this thing is less than or equal to 1. Another corollary that is pretty obvious, will not work on proving, which is probability of phi is 0. And then we go into a more interesting corollary. The probability of A union B in the general case is the probability of A plus the probability of B minus the probability of A intersect B. Intuitively, this sounds perfect. You would assume this is correct, right? Logically, yeah, you get A, you get B, and because you have had the intersection twice, when you add A and B, you take the intersection back, right? Side question, is my tone high enough for everybody? That the font is clear for everybody? Our colleagues in the back? Great. So, but this is how you prove things. You cannot just say, oh, intuitively it is like that. You prove things using things that you already know, theorems that you are already familiar with, that goes above this, and you use them to get to this. This is how you prove. And proofs, they don't have middle ground. It's either you prove something or you don't. The proof is either right or wrong. Of course, there could be a minor thing here or there, but the logic of the proof is either correct or incorrect. If you are asked to prove a general case, some relation for a general n, you prove it for n equals 3. That is not a proof, all right? So how can we prove this? Any suggestions? Let's look at this event, A and B. How can we decompose this event?
A different from B, B different from A, ters.
Awesome, thank you so much. It's 3 events, E1, which is A intersect B complement, exactly A set minus B, B complement intersect A, and E3 is A intersect B. The probability of A union B is then the probability of E1 union E2 union E3. And what is this probability? They are disjoint. We just did this disjoint scenario here, right? In the third axiom, right? So it is summation from I equals 1 to 3, the probability of AI. It's clear that the probability of this is going to be the probability of A minus the intersection. This one, B minus the intersection. You subtracted the intersection now twice. And then you will have plus the third event to give you finally P of A plus P of B minus P of A intersect B. And you put the square, everything is good. All right? Any questions? Okay. The more interesting, this one is already interesting, but the more interesting scenario here is to have a series of events, and this is a new corollary, that is C5, which is called the inclusion-exclusion principle. Another concept that can be taught from set theory, and it has a wide variety of applications. So you can use the inclusion-exclusion principle to calculate probabilities, which is what we will do right now. You can use it also to do combinatorics, to count. You can use it to do many, many things. Okay? So what is that concept? Like mathematically here, in the context of probability theory, the probability of union over AK is the summation from K equals 1 to N minus 1 to the K plus 1. Another summation, I1, I2, dot, 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 to IK, subset or equal to 1, 2, to N, the probability of the intersection from J equals 1 to K here, A, I, J. From the first glance, how many of you think this thing makes sense? We're not going to prove it or anything, so it's just that how many of you think, okay, that sounds pretty logical? Intuitively? Nobody? Okay, fine. Let's try to do it through an example. What exactly is this equation telling us? We want the probability of a huge union of events that has n events, not huge, n greater than or equal to 2, greater than or equal to 3 in this case, because we did the 2 case, and we want to calculate the probability. How can we go about it? How did we go about it here? we did the probability of the individual ones first and then subtracted the intersection. Okay? What will happen when you have 3 of them? You will have the probability of the individual ones A, B, C. And then you have over-added probabilities. You subtract the probabilities of the 2 tuples, A intersect B, A intersect C, and B intersect C. But then you over-subtracted, and you need to add what you have over-subtracted, which is A intersect B intersect C. Does that make the logic clearer now? This alternating sign exactly serves the same purpose, and it applies immediately to the name. Include, exclude. Include, exclude. Add, subtract, and so on. All right? So this is the logic of this equation. Does it make more sense now? Can we do together this, the probability of A1 union A2 union A3? What will this be?
A plus B plus C minus A intersection B minus A intersection C.
But with the probabilities, yeah.
Of course.
Exactly, thank you.
N plus probability of A intersection B intersection C.
Thank you. All right, a tricky question before we go on to the last corollary. A tricky question. Is there a general formula for how many terms you do here? Is there a general formula for how many terms produced by this probability? Thank you. Who was talking? Why is that? Because it's essentially summation from k equals 1 to n, and choose k. Right? 3, choose 1, 3, choose 2, 3, choose 3. Another question that is less tricky. Why is this thing equal this thing?
Number of subsets minus n.
What's that?
Number of subsets minus n.
No, I'm not talking about the set theory part of it. Now we did it together. I'm asking why is this thing equals 2 to the n minus 1?
I mean 2 to the n is number of subsets, right? That's why I'm saying it.
Yeah, true. I agree with you. Your logic is correct. But now I'm not even asking about the number of sets. I'm just asking about why this combinatorial summation equals 2 to the n minus 1. What's the fundamental reason behind that? Yeah, true, you are right.
Each element can be present or absent in a set, so there are 2 states for each element, and there are n elements to the power of n.
That's also correct, but that's from the perspective of set theory. I just want an algebraic answer. Why is this equal this? Will it matter to you if I write it like this? Does it matter? Does it change anything? So what is this?
Binomial.
Thank you. Exactly, right? That's a binomial. Binomial expansion. Right? Great. Last corollary, C whatever, 6. If A is a subset of B, then the probability of A less than or equal to the probability of B. The logic here is very similar to logic we have done before. We write B as B intersect A complement union B intersect A. What is B intersect A in this case? Exactly, it is going to be A. And thus the probability of B is the probability of something plus the probability of A. And thus the probability of A is less than or equal to the probability of B. Are there any questions? All right, let's take our 10-minute break and we will meet after the break.